Welcome student to our online chemistry class. Our chapter is halogen derivative. Now can you recall some concept? How are alkenes prepared from alkyl halide? And second is which is stronger base from the following? One aqueous KH or two alcoholic KH? Let us find out the answer of first question, and for this purpose we have to check the dehydrohalogenation reaction. So what is the meaning of dehydrohalogenation? D means to remove hydrogen and halogen from your alkyl halide. So name of the reaction is dehydrohalogenation. So up to this we will see some reaction in which the X group from alkyl halide get replaced or substituted by another nucleophile. So that's why these reactions are known as substitution reaction. But now we have to check elimination reaction. So let us see one reaction, that is here we see the alkyl halide, the carbon which is the carbon number 1, or it is also known as alpha carbon carrying a halogen, and next to that carbon is called as beta carbon or carbon number 2. So we remove the halogen from first or alpha carbon and hydrogen from beta or second carbon. So that's why this type of elimination is called as beta elimination or 1-2 elimination. So after elimination we get a double bond between these two carbon. So for this purpose we have to require a base that abstract the H plus from beta carbon, and then this electron pair between carbon and hydrogen is shifted between two carbon to form a double bond, and the electron pair between carbon and halogen goes with halogen as X minus, and we get BH and X minus and double bond between two carbon. So if you observe the alkyl halide, carbon number 1 and carbon number 2, both these carbon contain only single bond, so these carbons are sp3 hybridized, while in case of alkene both these carbon contain a double bond, so these carbons are called as sp2 hybridized carbon. So that is the main difference. So here we remove the group, so that's why name of the reaction is elimination, and we remove the hydrogen and halogen, that's why the name is dehydrohalogenation. So here for removal of this HX we require a base, and here we prefer a alcoholic KOH. Okay, alcoholic KOH is the base for this reaction. Now let us consider the elimination reaction in 2-chloro or 2-bromo-butane. Here we take 2-bromo-butane. So bromine is present on this carbon is alpha carbon. Next to that is CH3. So this carbon is beta carbon. On left hand side there is CH2 and CH3. So this carbon is also beta carbon. We call this carbon as a beta 1 and this carbon as beta 2 for our understanding. So when we write a reaction with alcoholic KOH, then Br is removed from alpha carbon and hydrogen is removed from any one these two beta carbon. So if we remove the hydrogen from this beta 2 carbon, then the double bond is in between this alpha and beta 2 carbon. So we get CH2 double bond CH and C2 H5 or CH2 CH3 as it is. Double bond is present on first carbon, so we get but 1 in as a product. But if we remove the hydrogen from beta 1 carbon and halogen from alpha carbon, then what we get? The double bond is present between alpha and beta 1 carbon, and remaining thing is as it is. by removing Pr from alpha and hydrogen from beta 1. The double bond is in between second and third carbon. So what we get? Bu2E as a product. So now we have to decide which product is major product, and for that purpose one rule is there, and that is set-zep rule. So what is set-zep rule? That we have to check. So in dehydrohalogenation reaction, the preferred product is that alkene which has greater number of alkyl groups attached to doubly bonded carbon atom. So now again we go to our reaction. If you observe these two products, but1ene, in which double bonded carbon contains, first carbon contains 2 hydrogen, so there is no substance. On second carbon there is one substance, that is CH2, CH means ethyl group, and one is hydrogen. So only one substance or alkyl group is present on double bonded carbon. So this carbon contains one alkyl group, so it is a monosubstituted alkene. But if you observe but2ene, both carbon number 2 and carbon number 3, they contain one hydrogen and one methyl group as a substance respectively. So there are overall 2 alkyl groups attached to carbon-carbon double bond. So it is a di-substituted alkene. So according to set-zep rule, the major product is more substituted alkene. So but2ene is the major product. So if you observe the percentage, 20% of but1ene and 80% of but2ene is the product yield. So major product is but2ene for this beta elimination. And if you observe the stability order, then we observe that, so this R2C double bond Cr2, there are 4 alkyl groups, so it is tetrasubstrate. It is highly stable. Then this compound R2C double bond CHR, it contains total 3 alkyl groups, so it is trisubstrate. It is less stable than tetrasubstrate. Next, that is R2C double bond CH or RCH double bond CHR. Both these compounds contain total only 2 alkyl groups, so it is disubstituted. And last group RCH double bond CH contain only one R alkyl group, so it is monosubstituted. And least stable is CH2 double bond CH2. It does not contain any alkyl group, so it is 0 substituted. So this is the stability order of alkyl halide. After that we get a alkene, and due to which reaction? Elimination reaction. So according to set-zep elimination, formation of more highly stabilized alkene is a stable product or preferred product during elimination reaction. This is according to set-zep rule. So there is one another question. Do you know the distinguish between elimination and substitution? So alkyl halide undergo substitution as well as elimination. Both the reactions are brought about by basic reagent. So hence there is always a competition between these two reactions. The reaction which is actually predominant depends on some factors. So let us see these factors. First is nature of alkyl halide. Tertiary alkyl halide prefers to undergo elimination reaction, whereas primary alkyl halide prefers to undergo substitution reaction. Then the strength of that nucleophile and size of nucleophile. So bulkier electron rich species means like your tertiary butyl group prefers to act as a base by abstracting the proton and thus favors elimination. Substitution is favored in case of comparatively weaker base. which prefers to act as a nucleophile. And third one is the reaction condition. So less polar solvent, alcoholic KOH means KOH is dissolved in alcohol. So alcohol is not a polar, so it is less polar. High temperature favors elimination, whereas low temperature and polar solvent means KOH is dissolved in water, that is aqueous KOH, favors substitution. So for elimination reaction we require strong base. So alcoholic KOH is strong base than aqueous KOH. This is the answer of your second question. Now next one is the reaction with active metals. There are different active metals such as sodium, magnesium, cadmium. They readily combine with alkyl chloride, bromide and iodides to form the compounds containing carbon metal bond. So the compound which contain carbon metal bond is known as organometallic compound, because there is a organic part as well as metallic part. So such a compound are organometallic compound. So let us see first reaction with magnesium. When this alkyl halide is treated with magnesium in presence of dry ether as a solvent, it gives alkyl magnesium halide. Let us see the reaction. Rx plus Mg, alkyl halide react with magnesium in presence of dry ether, gives RMgX. So we get a alkyl magnesium halide, and it is also known as Grignard reagent. So it is very reactive compound. It reacts with water, methyl alcohol and ammonia, and they gives hydrocarbon, that is alkane, as a product. So let us see the reaction. When Grignard reagent RMgX react with water, it gives RH plus MgXOH. We get higher alkene. This, let us see, R is equal to CH3, then we get CH3H means methane is a product. When RMgX reacts with methyl alcohol, CH3OH, it gives hydrocarbon plus MgXOCH3. And when RMgX react with ammonia NH3, it gives RH plus MgXNH2. So if we change the reagent, then byproduct will get changed only, but our main product is RH. So this is the use of Grignard reaction, and for this purpose the scientist Victor Grignard received a Nobel Prize in 1912. So if you observe the alkyl magnesium halide RMgX, carbon in Grignard reagent has negative polarity. So if we write the partial poles, so R carrying delta negative charge because it is more electronegative than Mg. So Mg carrying delta positive charge, so it acts as a nucleophile. Alkyl group from Grignard reagent acts as a nucleophile, and it will attack on electron deficient center to give different products in organic synthesis. Now let us see the reaction, Wood's reaction. So alkyl halide react with metallic sodium in presence of dry ether as a solvent. It gives higher alkanes containing double the number of carbon atoms present in your alkyl halide. So let us see Rx. It is alkyl halide react with sodium metal in presence of dry ether. So this X from alkyl halide react with sodium and it gives 2NX. So one R group from one molecule of alkyl halide react with second R group of another alkyl halide to give R dash R. So here number of alkyl groups get doubled, or number of carbon atoms in your alkyl halide get double if you choose one type of alkyl halide. So for example, if R is C2H5, then C2H5Br reacts with sodium metal in presence of dry ether, we get C2H5-C2H5 or CH3CH2CH2CH3. So all carbon in single line, so it is N-butane plus 2NaBr is the byproduct of this reaction. So if you take only ethyl bromide, we get N-butane as a product, and if we take methyl bromide, then we get ethane as a product plus 2NaBr. So if you choose only one alkyl halide, then we get an alkane, higher alkane having double carbon than your alkyl halide. So we get even number of alkanes. But when we have to prepare odd number of alkanes such as propane, then we have to choose two different types of alkyl halide. One is CH3Br methyl bromide and another is ethyl bromide. So when both these compounds react with sodium metal, then methyl bromide can also react with methyl bromide and it will produce ethane as a product. Ethyl bromide can react with another molecule of ethyl bromide and it gives N-butane as a product, as we see in above reactions. And methyl bromide can react with ethyl bromide to produce propane. So when we have to prepare a propane as a product by this wood synthesis, we can't get only propane as a product, but along with that we get ethane and N-butane as a product also. So this is not the good method for preparation of propane, because there are three alkanes and the properties of these three alkanes are nearly same, so it is very difficult to separate your main product propane from ethane and butane. This is not the good method for preparation of odd number of alkenes like propane, but it is very good method for preparation of even number of alkanes such as ethane or N-butane. So this is the drawback of your wood synthesis. Then next is the reactions of haloarenes. So reactions of haloarenes with metal such as sodium metal. So it is quite similar to your wood synthesis. In wood synthesis we use alkyl halide. Here if we use alkyl halide and aryl halide such as methyl bromide and bromobenzene react with sodium metal. So this Br from both this alkyl and aryl halide react with sodium to give 2NaBr, and this alkyl group methyl react with benzene ring and it will produce C6H5CH3 and the product is methyl benzene or toluene. So here in your product alkyl and aryl group both are present, so that's why the name is Woods fatigue reaction. But if we take only aryl halide such as chlorobenzene or any halobenzene as a reactant, they react with sodium metal in presence of dry ether. The Cl goes with Na and one phenyl ring react with another phenyl ring, like R react with another R, and it gives biphenyl as a product. Then such a reaction is called as fatigue reaction. Then next is nucleophilic substitution, or it is also known as SN reaction, that we already known, and these reactions are called as SN reaction. But now we have to check the SN reactions of haloarenes or aryl halide. So can you recall what is the resonance? So there are some terms that you already learned in 11th standard. So for revision purpose you can refer to standard 11 chemistry textbook section 14.6.6. You can follow the page number 200 and 28. Okay, then draw the resonance structure of bromobenzene and identify the types of hybridization of carbon to which halogen is attached to haloarene. So if you observe the resonance structure of chlorobenzene, let us see. This is the resonance structure of chlorobenzene. Instead of chlorine, only there is a Br, then we can write the resonance structure of bromobenzene. So if you observe here, a lone pair or chlorine, one of them get shifted to carbon chlorine bond and we get a double bond here. So as lone pair of chlorine is used, chlorine carrying positive charge and the electron pair between these two carbon gets shifted to this carbon. So we write the carbon numbers. This is the carbon number 1, and this is the carbon number 2. The electron pair between carbon number 1 and carbon number 2 shift to carbon number 2. Carbon number 2 carrying negative charge and chlorine carrying positive. In the next resonating structure, this electron pair on carbon number 2 gets shifted between carbon number 2 and 3, and the electron pair between carbon number 3 and 4 gets shifted to carbon number 4. Carbon number 4 carrying negative charge, and in next resonating structure, the negative charge on carbon number 4 shifted between carbon number 4 and 5, and negative charge is shifted to carbon number 6. Okay, and in last structure, again the electron pair from carbon number 6 is shifted between carbon number 6 and 1, and again the double bond between carbon and chlorine is shifted to chlorine, and chlorine again carrying that lone pair. So there is a movement of this lone pair from chlorine to again chlorine through this benzene. So if you observe resonance structure first and resonance structure 5, it is identical, but only the change in the position of double bond. And in structure number 2, the negative charge is on second carbon. In structure number 3, negative charge on fourth carbon, and in structure number 4, the negative charge is on fifth carbon. So if you observe, this resonance effect, the carbon of this benzene ring is sp2 hybridize. So it shows low reactivity towards the nucleophilic substitution reaction, because if you observe this different resonating structure, carbon number 2, carbon number 4 and carbon number 6, they contain negative charge, means these positions are electron rich position, the nucleophile cannot attack. So your aryl halide shows low reactivity towards nucleophilic substitution reaction. So one more reason is that the carbon-chlorine bond in chlorobenzene is stronger and shorter than chloroalkane. C-cell bond in chlorobenzene is 169 picometer as compared to carbon-chlorine bond length in alkyl chloride is 178 picometer. So it is difficult to break, and after breaking this, the group is known as phenyl and the positive charge is developed. So we get a phenyl cation produced due to self-ionization of haloarene will not be stabilized by resonance. So there is no formation of carbocation. So this is the main condition of SN1 reaction. So we can't write the SN1 matrix for this stage. Then we cannot attack the nucleophile from backside by this bulkier aromatic ring because it is exactly opposite to your living group. So this also rule out the SN2 mechanism, because in SN2 mechanism backside attack is the important thing. So due to these factors, the aryl halides are difficult to undergo nucleophilic substitution. So if you observe the nucleophilic substitution reaction, cleavage of CX bond in haloarene proceeds with difficulty. But if there are certain groups at a certain position of this benzene ring, they increases the electron density or they decreases the electron density. If you observe the halogen of aryl halide, it increases the electron density. That's why it is called as activator, and it activates the ring towards the substitution. So for example, presence of electron withdrawing group at the ortho and para or para position increases the reactivity of haloarene towards this substitution of halogen atom. Greater the number of electron withdrawing group at ortho, para or ortho and para, greater is the reactivity. So let us see the reaction. So if you observe this, the para nitro chlorobenzene, it reacts with NaOH and this Cl gets substituted by OH. So it is nucleophilic substitution followed by hydrolysis. This reaction takes place at 413 Kelvin. If there is a one NO2 group at para position, the temperature is 433 Kelvin. So if the number of withdrawing group NO2 group increases, in previous case only at para position, but now if we introduce at ortho position also, then temperature decreases. That means this withdrawing group increases the electron density of your compound. So 2,4-dinitrochlorobenzene is more reactive than para-nitrochlorobenzene. And if we increase one more NO2 group or withdrawing group, then there is no need of heating. Simply warm condition is required and we get a product, and we get a 2,4,6-trinitrophenol is a product. If we check the reagent also, when there is only one withdrawing group, strong base NaOH is required. If there are two NO2 withdrawing groups, then aqueous Na2CO3, which is weaker base than NaOH, is the reagent. And if there are three NO2 group, then there is no need of your base. So this indicates that reactivity of your compound, or here aryl halide chlorobenzene, goes on increasing if we increases the number of groups. So 1 NO2 group, 2 NO2 group and 3 NO2 group increases the reactivity of chlorobenzene. But If your electron withdrawing group is at meta position, there is no effect on the reactivity. Remember this. So, if you observe the simple conversion of chlorobenzene to phenol, reaction takes place at 623 Kelvin and 300 atmospheric pressure. So, from this, you can easily understood that increasing the electron withdrawing group at ortho and para position or both ortho and para, then reactivity of your halobenzene goes on increases. So keep in mind, this is important for your board exam. So this can be understood by using the resonating structure. So para nitrochlorobenzene. So if OH group is attached on this carbon, first carbon, then the electron pair between first and second is shifted to second carbon, and when in the next resonating structure this negative charge on fourth carbon can transfer to oxygen of NO2 group. So we can write one more resonating structure, which is the third resonating structure. So again this negative charge from oxygen is shifted to this carbon, and again it is involved in the ring. So your withdrawing group at para position as well as ortho position participate in the resonance. So due to that, reactivity of your compound increases. So it extends the conjugation. So the intermediate carbanion means carbon carrying negative charge, it's better stabilized, which favors the nucleophilic substitution. So you can easily understood this with structure number 3. Now this is about the nucleophilic substitution. So at normal condition, haloarenes does not prefer to undergo nucleophilic substitution, but if there is a electron withdrawer group such as NO2 group at ortho, para or both ortho and para, then the reactivity of that haloarenes goes on increasing. Now next reactions are electrophilic substitution or AC reaction in aryl halide. So for that purpose you must know what is electrophile. So you can refer standard 11 chemistry textbook 14.6.2 section and page number 223. You can write some examples of electrophile: Cl plus, NO2 plus, CH3 plus. These are some electrophile. So what type of reactions are observed in case of benzene? So for that purpose you have to refer standard 11 chemistry textbook section 15.4.6 and page number is 254. So let us see that reactions of benzene. So if you observe the reactions of benzene substitution reaction, these are some electrophilic groups: Cl, Br, NO2, SO3H, alkyl group, COR, acyl group, and we can write the reactions. So chlorination, bromination. For chlorination and bromination, the electrophile is Cl plus and Br plus. And to generate the electrophile, we require FeCl3, FeBr3 as a catalyst. Then for nitration, we use nitrating mixture. For sulfonation, we require oleum, and for alkylation, we use alkyl halide in presence of anhydrous AlCl3. So these are some reactions of your benzene. So that you already learned in 11th standard. But when there is a monosubstituted or halosubstituted benzene, then this is the chart. So when your electrophile will attack on your benzene ring, substituted monosubstituted benzene ring, so the hydrogen from ortho position get replaced and we get ortho substituted benzene as a product, halobenzene as a product, or we get para substituted halobenzene as a product. So for this purpose you must familiar with which groups are ortho para director and which group is meta director. So if the group is ortho para directing group, that helps for your substitution at ortho and para. Which groups are ortho para directing? Cl, Br, OH, OCH3, NH2, NHR, NR2, alkyl group CH3, C2H5. So these groups which direct the incoming group to ortho and para position. That's why these groups are ortho para directing. Why these groups are ortho para directing? That we have to check with the help of the resonating structure of chlorobenzene. So if you observe the resonating structure of chlorobenzene, if you observe this second structure, the negative charge at ortho position or carbon number 2, in next resonating structure, the negative charge at fourth position of your benzene ring, and in next structure again negative charge is on 6 carbon or ortho position. So your ortho and para position become electron rich. That's why Cl is a ortho para director. Similarly, if you observe the resonating structure of phenol, in that OH group again contain lone pair of electron or oxygen, and if it is shifted towards the benzene ring, you can observe ortho and para position becomes electron rich. So OH group also increases the electron density at ortho para position of your benzene ring, so it is a ortho para director. So ortho and para positions have a greater electron density than the meta position. So OH group, Cl group or X group activates the benzene ring for attack of second substituent, which is a electrophile at this electron rich center. Which is electron rich center? Ortho and para. So all ortho and para directing group possess non-bonding electron pair or lone pair on the atom which is directly attached to aromatic ring. Okay. So in case of aryl halide, the halogen atoms are moderately deactivated because of their strong minus I or electron withdrawing inductive effect. Overall density on that benzene ring decreases due to this minus I effect. So it makes the electrophilic substitution difficult, but due to the resonance structure, the electron density on ortho and para position is greater than the meta position. So halogens are orthoparadict. So here resonance is greater than the inductive effect of aryl halide. Okay, so if there is a Cl group in your benzene ring as a substituent, then your next substitution will take place at ortho and para position because Cl is a ortho para director. So now we will understand the electrophilic substitution in aryl halide. So let us see the reaction. So before that, So aryl halide prefer to undergo electrophilic substitution reaction slowly as compared to benzene, because there is a halogen and it shows minus effect. So in resonance structure of chlorobenzene, electron density is relatively more at ortho and para position. Therefore, incoming group is more likely to attack at this position, but due to the steric hindrance at ortho position, para product usually predominates. So para product is the major product. So in haloarenes, halogen atom has a strong electron withdrawing inductive effect. This deactivates the ring and electrophilic substitution reactions occur slowly as compared to simple benzene. So let us consider halogenation. For chlorination, we require chlorine. So when chlorine react with chlorobenzene in presence of anhydrous FeCl3, substitution at ortho and para will take place. So we get 1,2-dichlorobenzene and 1,4-dichlorobenzene. Out of that, 1,4-dichlorobenzene is the major product. So which is the major product? 1,4-dichlorobenzene. This is major product. 1,4-dichlorobenzene is a major product. So you have to write the balanced chemical equation. It's not balanced, so write down here 2 chlorobenzene and for balancing 2HCl. Always write the balanced chemical equation. So reagent is chlorine in presence of anhydrous FeCl3. Now next reaction, that is nitration of chlorobenzene. The reagent is nitrating mixture. What is nitrating mixture? It is a mixture of concentrated nitric acid and concentrated sulfuric acid. So the hydrogen at ortho and para position react with OH from nitric acid, and these hydrogens get replaced by NO2. So we get 1 chloro 4 nitro benzene when hydrogen at para position is replaced. If hydrogen is replaced from ortho position of chlorobenzene, we get 1 chloro 2 nitro benzene. So due to steric hindrance, the para substituted product is the major. That's why 1 chloro 4 nitrobenzene is the major product. Remember the balancing the reaction. For balancing, you have to write 2 chlorobenzene and byproduct is 2H2. So always write the balanced chemical equation. Now for sulfonation, sulfonation means substitution of SO3H group. We require oleum. What is oleum? It is fuming H2SO4 or H2S2O3. How will you write the reaction to form oleum? When sulfuric acid reacts with sulfur trioxide SO3, it gives oleum, and that oleum or fuming H2SO4 react with chlorobenzene, it gives substituted product. So substitution will take place at ortho with respect to this chlorine and at para. So 1,4 position we get a substitution, but while writing the name of this, we have to change the numbering. The SO3 group H carbon is carbon number 1 and the next carbon is second carbon, because there are order, and according to this order, SO3H group has first priority than the Cl in the nomenclature of IUPAC system. So we get 2 chlorobenzene sulfonic acid and 4 chlorobenzene sulfonic acid. Among that, 4 chlorobenzene sulfonic acid is the major product. Then if we have to substitute the alkyl group, then for example methyl chloride is the reagent, then we can substitute the hydrogen from ortho and para by this methyl group and we get 2-chlorotoluene and 4-chlorotoluene as a product. Among that, again 4-chlorotoluene is the major product. You can write their another names. So for 2-chlorotoluene, 1-chloro-2-methylbenzene is the another name, and for 4-chlorotoluene you can write 1-chloro-4-methylbenzene as a alternative name. So for balancing, you can write here 2HCl. Then if you have to substitute acyl group, then acyl chloride is the reagent and it is CH3COCl. It reacts with chlorobenzene in presence of anhydrous AlCl3. So we get 2-chloroacetophenone and 4-chloroacetophenone. Among that, 4-chloroacetophenone is the major product. For balancing, you have to write the numbers and 2HCl as a byproduct. Okay, so this is about the reactions, nucleophilic substitution and electrophilic substitution. Aromatic compound generally prefer electrophilic substitution reaction. Then last point is the uses and environmental effect of some polyhalogen compounds. So let us see the first compound, dichloromethane or methylene dichloride. The compound is CH2Cl2. There are some properties which are shown with yellow color. The uses are shown with green color, and the side effect or environmental effect are shown with pink color. So you can easily understood. So dichloromethane is colorless volatile liquid with moderately sweet aroma. Aroma means odor, and it is used as a solvent, and it is also used as a propellant, means it is a fuel in aerosol. Then there are some side effects. Dizziness, means in Marathi chakkar yene, fatigue means thakwa, nausea means मळमळ, headache means डोकेदुखी, numbness means सुन्नपणा, आणि weakness means अशक्तपणा. It is highly dangerous if it comes in direct contact with eyes. So if it is come in contact with eyes, it causes danger or damages the cornea. So this is about the first compound. Then second compound is chloroform, CHCl3, or IUPAC name is trichloromethane. Then which are the properties? It is colorless liquid with again a sweet smell. It is used to prepare chlorofluoromethane. Compound is CH2ClF, and it is also known as refrigerant R20. What is the use? It is used as a solvent for extraction of natural product like gum, fats and resin. It is also used as a source of dichlorocarbene. Then chloroform causes depression of central nervous system when it affects, and on inhaling the chloroform for short time it causes fatigue, dizziness, headache. If we expose for long period to chloroform, it may affect on our liver. And one important thing is that when it is exposed to air and light, it forms a poisonous compound phosgene. So it is toxic compound, and to avoid this, the chloroform is stored in dark colored airtight bottle. So on the basis of this point, there is always a reasonable question: why chloroform stored in dark color airtight bottle? The reason is to avoid the exposure to air and light, because when it is exposed it forms poisonous scorching gas. So remember this point. The next compound is carbon tetrachloride CCl4. The IUPAC name is tetrachloromethane. The properties is, again, it is colorless liquid with sweet smell. And what is the uses? It is used as a solvent for oil, fat and resin. It serves as a source of chlorine. Then it is also used as cleaning agent. And what is the side effect? It is highly toxic to liver. When exposed to high concentration, it can affect central nervous system, and it is suspected to be carcinogenic, means toxic. Prolonged exposure may cause death. So it is also one of the greenhouse gas. Remember that this may be asked in MCQ. Then next one compound is iodoform CHI3. IUPAC name is triiodomethane. It is yellow crystalline substance with disagreeable smell. And what is the use? It is used as a medicinal purpose for healing the wound, and that's why it is called as healing agent. It is also used as an antiseptic in the dressing of wound, but the use is for limited purpose. Then what is the side effect? It causes irritation to skin and eyes. It causes respiration or breathing difficulty, dizziness, nausea, depression of central nervous system, and it may disturb the visual system. Then next compound is freon. So these compounds are also known as chlorofluorocarbons, and it contains chlorine and fluorine. So that's why chlorofluorocarbon. The most common compounds are difluoromethane, that is CCl2F2, freon 12. Then chlorodifluoromethane, that is CHClF2 R22, and trichlorofluoromethane R11 CCl3F. These are different freons. What is the uses? They are used as a refrigerant in fridges, air conditioning, propellant in aerosol, and they are also used as solvent. They are used as a blowing agent in making the foams and packing the materials. What is the side effect? They are responsible for ozone depletion of ozone in stratosphere. Then on regular large quantity inhalation of these freons, they results into breathing problem, organ damages, and loss of consciousness. Then to go through this. Then next compound is dichloro-diphenyl trichloroethane. It is also known as DDT. This is the short form of this compound. It is a colorless, tasteless, odorless crystalline compound having insecticidal property. So due to this property, it kills the insect such as houseflies, mosquitoes, body lice, and it was used for controlling the malaria and typhus. Then what is the side effect? When exposed to high doses, there may be vomiting, tremors, shakiness. Then laboratory animal studies shows that there may be adverse effect on liver and reproductive system. Then it is a persistent organic pollutant, so it readily absorbs in soil and tends to accumulate in the ecosystem. When It is dissolved in oil or other lipid. It is readily absorbed by the skin. So it is resistant to metabolism. It accumulates in fatty tissues. And therefore, it is banned to use as a insecticide. So this is the structure of your DDT. So we'll stop here. Remember these uses, then side effect of this haloarenes and the alkyl halides.